Forging is taking on new dimensions. Increased widths and lengths to near-net shapes will soon be a reality. The operation you will see not only will meet most of the expectations of a 200,000-ton forging press, but will surpass them. Complete wing panels, long-varying cross-section extrusions, space vehicle structures, plus other commercial applications will be formed in a fraction of the time presently required with today's technology. A new development with the difference, called flow forge, forms metal by squeezing it to conform to a die cavity as is done conventionally. The difference with flow forge is that the male portion of the die is segmented, and each segment is forced down into the material to be formed, which is resting in the female part of the die. When all of the male segments reach the end of their travel, the resulting cavity between the male and female portions of the die is filled with the material. Let's take a look and see how flow forge works. The segmented male die rests on the material contained in the female. As the die assembly moves past the inclined plane, the male segments are gradually forced down in sequence, a predetermined amount. When finally past the inclined plane, the part is formed and ready for extraction. Here you see the detailed configuration of these parts and how close to the final shape they are. These parts, although limited to a plan view of 3 by 8 inches and a height of almost 1.5 inches, can be easily scaled up to form larger and longer parts. This statement can be made with confidence, since the power requirements to make a 3 by 8 inch part will be the same as making a part of any length. The power requirement does not change because the male segments are forced down sequentially, a small group at a time. All that is needed is a hydraulic cylinder with a greater stroke to pull a longer die past the inclined plane. With the flow forge system, forming and shaping parts becomes a very simple operation and is easily repeated after the required parameters are established. Let's look at this simple operation. The die components, male and female, are coated with a high-temperature lubricant. Each coating will survive the squeezing of several parts. At this time, the material to be formed is also coated. The female portion of the die is placed in the machine die container, ensuring that ejection pins in the female are properly seated. The material to be formed is placed into the female, and the male die segments positioned over the material. End wedges are positioned and secured to ensure precise downward motion of the male segments. Now we obtain a reading where the male die segments are all resting on the material to be formed. This is the reading from which all penetration dimensions are made. This reading is obtained by lowering the upper platen by motor until it almost touches the die assembly. The rest of the downward motion is done manually to get an accurate starting position. When this position is obtained and recorded, the die assembly is retracted from the inclined plane and placed on the oven bed, where the thermocouple cables are positioned. A switch is then activated to lower the oven over the die. Power for the oven is switched on, and the temperature controller is set. While the die and material are being heated, the upper platen is lowered to provide for proper penetration. The initial lowering of the platen is motorized. Then manual lowering will control the penetration to within 1/1000th of an inch. The aluminum alloys to date include 2024, 6061, and 7075. A soak time of 1 hour at the required temperature has worked very well for the 5 different configurations forged to date. At the proper time, the oven is raised. One of the thermocouples remains in the die cavity to monitor the temperature during the forging process. The die is advanced to the work area, where a shear pin is used to secure the die to the power cylinder. A 5-horsepower motor that drives a 3,000 psi pressure compensating pump is started, and a hand-operated switch retracts the piston of an 8-inch diameter cylinder, which gradually but firmly pulls the die assembly past the inclined plane. It takes 20 seconds to form an 8-inch long part. A unique feature of the Flowforge system is the ejection ramp that gradually lifts each male segment from the female as soon as the part is forged. As the die assembly leaves the flat portion of the inclined plane, the roller bearings on each male segment roll up on 2 inclined rails to easily and smoothly remove all of the male segments from the female. These segments roll onto a platform and remain there while the die cavity returns to the loading station to eject the part. For these prototype applications, part ejection is simplified by removing the female die from the machine die cavity and placing it in a simple hand-operated hydraulic rig where the ejection is done. Less than 2 minutes has elapsed since the die assembly left the oven station, the part forged and ejected. This part has ribs on both sides. All the edges and corners are as sharp as intended. After removing approximately 2% flash, this finished part demonstrates the accuracy of the Flowforge process. Physical property analysis revealed tensile specimen test values to be consistent and within specifications. These forged parts demonstrate the versatility and potential of the Flowforge process. This waffle section was the first design to be forged and was used to prepare specimen for physical and metallurgical tests. 3/4 of a degree draft was used for all of the parts Flowforged. Let's look at a wooden model of a production-type Flowforge machine. The process is so rapid, it can keep several furnaces busy heating dies and material. The major difference between this model and the prototype is that the compression sidewalls are equipped with indexing holes. To avoid the expense and limitation of using a fixed large cylinder with a long stroke, a system of indexing holes in the side plates allows for a shorter cylinder to index back and forth as required. A standard cylinder with a short stroke can be used to forge parts of any length. Movable furnaces are included as part of the system to effectively move large dies quickly and easily between the furnace and the inclined plane. All of the force required in shaping the material is performed at the inclined plane, and the power needed is only a fraction of that required by conventional forging equipment. In addition, the localization of pressure in this sequential manner results in improved material flow and excellent filling of the die cavity. Photos taken of the grain flow of one of the more difficult shapes substantiate the excellent results of material flow with no indication of lapse or folds. This massive amount of steel, 35 feet above ground, with a 70-foot foundation to contain the multiple large diameter cylinders, plus a pumping station and large holding tanks, requires a great deal more space than a Flowforge system. The Flowforge system has a maximum height of only 10 feet, with nothing below ground. If there is a requirement to make larger parts, the inexpensive revision is to merely add side plate extensions. Power requirements do not change. The one cylinder required for the Flowforge system is mounted on the power tray, along with an electric motor, pump, and a hydraulic storage tank. The power tray comes completely assembled as a unit and is easily installed and serviceable. One electric cable connects the power tray to the system. Our projections show that Flowforge systems can be fabricated in various sizes with virtually no limitation for expanding size or capacity. The power rating for Flowforge equipment is in tons pull, as compared to tons for standard hydraulic equipment. As an example, the MMF-72, a 6-foot wide system which is rated at 2,000 ton pull, can forge a 5-foot wide by 20-foot long wing to near net shape. Conventional equipment would require a 350,000 ton press. This MMF-72, at a projected cost of $10 million, is considerably less than the estimated cost of the 200,000 ton press the Air Force has been seeking for years. The work performed has demonstrated the versatility and potential of the Flowforge system over conventional large systems. The advantages we can look forward to are less costly to design and fabricate, less costly to install, operate, and maintain, more energy efficient, greater material savings. One cycle shapes the part to very near net shape. We are confident that in the future, JM Enterprises, with the Flowforge, will make larger and longer parts to closer tolerances than ever thought possible, and at a fraction of today's costs.